passed, so it's time for our last talk before lunch, everyone. So we really should make a start now. Our next speaker is here to talk about the Gilectomy and how it's going. Please make welcome Larry Hastings.
Thank you. My name is Larry Hastings. Ladies and gentlemen, boys and girls, children of all ages, this is the Gilectomy. How's it going? PyCon 2017 edition. I call the talk that because when I go to conferences now, people walk up to me and say, "Oh, Larry, oh, you're the guy working on the Gilectomy. How's it going?" And I'm like, I'm about to speak for 40 minutes about how the Gilectomy is going, and I don't want to answer for 40 minutes every person who walks up to me at a conference. So I'm going to do it for everybody all at once, and now you don't have to ask that question. You can ask a more specific question. So about this talk, I want to warn you, just like last year, I gave a talk about the Gilectomy last year, an introductory talk. This is kind of the same preface slide. This talk will be exceedingly technical, and it's going to assume that everybody in here is comfortable about me talking about multi-threading issues and about CPython internals. This year, I'm kind of assuming that you're mildly familiar with like maybe my talk from last year, so there's a lot of stuff that I'm not going to explain. I'm just going to dive right into some of these concepts. If you want to know more, you can watch my talk from 2 years ago, Python's infamous GIL, where I explained the GIL itself, and then last year's talk where I kind of got started, the Gilectomy removing Python's GIL. So the GIL, the goal of the Gilectomy, or the GIL of the Gilectomy, I want to run existing multi-threaded Python programs, so a Python program you could write today using the threading module. I want to run it on multiple cores simultaneously. I want to run it with as little I want to implement this with as little C API breakage as possible. It's impossible to not break the C API. There are some guarantees the GIL gives you that I cannot guarantee anymore. But with as little breakage as possible. And I want to run it faster than CPython does with a GIL by wall time. So this is if you had a stopwatch and you started your program running, when it finishes and you hit it again. If the program ran faster, then I will declare the Gilectomy a success, which it has never done. The approach that I'm taking, and again, this was most of the talk last year, Python uses reference counting for tracking the lifetimes of objects, and I switched that to atomic increment and decker. That's something that your Intel CPU does for you, where it will increment or decrement a number stored in memory in an atomic way, such that there are no race conditions. You're guaranteed that after you're done, the number has been incremented by 1, and it was done in a safe manner. I used I added locks to all the internal data structures inside of Python objects that are mutable, like dicts and lists, so that those operations are safe. If you append to a list or you add set an item on a dict, that has to be an atomic operation. It has to be safe. And so those objects lock themselves internally. I also added a bunch of locks around a bunch of internal C data structures that are used inside of CPython, like free state. But there's two in particular I want to call out. Obmalloc, which is what we call the small block allocator. This is used for memory allocation for small objects, which is like under 256 bytes or something. I don't remember what the cutoff point is. But this is used for most of the objects that are allocated inside of CPython. And this is very finely tuned, and it's super fast. And CPython relies on it being fast. And adding locking to that in order to make it safe has slowed it down a great deal. Also, there are a bunch of free lists inside of CPython. It's very handy if you're using a bunch of, say, integers or frame objects. If you allocate a fresh one every time, that's a little slower than just say, oh, the last one that I use, I'm going to put it on a list and then reuse it next time I need a frame object or an integer or something. So there are a bunch of free lists internally of Python objects that get reused constantly. And I, of course, had to put locks around those data structures or make them per thread. I also disabled the garbage collector entirely. I'm just not ready to deal with the garbage collection under the Gilectomy. There's a lot of research. There are absolutely thread-safe, multi-threaded friendly garbage collection algorithms. That's going to be a lot of work, and that's not the thing that interests me. What interests me is getting Python to be fast enough that this is useful for somebody ever. So my general approach is I got it working, and now I figure out what the slowest thing is, and I run it under a profiler, or I come up with thought experiments, and I experiment, and I try something, and I see if I can make it go faster. If I make it go faster, then I keep it. If then it doesn't go faster, then I don't throw it away. I may like put it on the back burner and try it again later, because sometimes you turn a corner, and now this technology is going to work again. Just to give you an idea of how crappy this project is, my official benchmark that this is literally all the code I ever run under the Gilectomy is a really bad Fibonacci number generator. It's a recursive Fibonacci. So this is exercising an if statement. It's exercising some math. It's exercising recursive function calls and, of course, bytecode and a bunch of internal stuff inside of the Python engine. But this is all I ever run. So I'm running on this on multiple cores simultaneously inside of CPython. So an overview of what's happened since last year when I gave the Gilectomy talk. We start with what I'm going to call last June's version of the Gilectomy, the atomic version for using atomic Inker and Decker. I switched to something called buffered reference counts, which was done by about October. And then I did a bunch of work on obmalloc, and that was done in about April. And then just this month, I did some work that I'm calling no TLS. TLS, when I say TLS, what I mean is thread local storage. This is data that you can store per thread so that each thread has its own version of something. You need that in order to, you can store something there and no other thread is going to examine it, and so you don't have to lock it in order to talk to it. So I'm going to go through each of these items and basically what it is, and I'll show you how much it got faster. But I want to talk for just a moment about how benchmarking is impossible on modern computers. As Victor talked about in his talk this morning, modern CPUs, like an Intel CPU, like a Xeon, has this speed step technology where it's constantly adjusting the speed of the cores inside of your CPU. And so I have a computer that literally has like 56 cores. It's an enormous server. And this is some of the cores at a particular moment in time, how fast they're running. So you can see, I was running a benchmark at the time, so the ones in the lower right are the fastest ones. They're running at 3100 megahertz. The slowest ones are running at 1200 megahertz. You really don't know from moment to moment how fast your CPU core is running, and so it makes it almost impossible to do meaningful benchmarks in any meaningful way. So this is just to give you an idea. Like, already my benchmarking is crappy. They're even crappier because of this. I haven't figured this one out yet. Victor says, oh yeah, there's a way you can turn it on for Linux. We'll figure it out. But that's just a proviso to give you the sense of, let's look at the benchmarks from a sort of a 10,000 foot view. Let's not get concerned about like 5% this way or another. So this is a graph of the speed of the Gilectomy versus stock CPython. And again, I'm talking about different eras. So I'm going to update the graph every time I do a new thing. So the red line at the bottom is stock CPython, which was the base revision that I started the Gilectomy against, which was last February. It was trunk, so it's what became 3.6, but there was a lot of work put into 3.6 after I branched. And then the blue line is the Gilectomy. The bottom, the x-axis is the number of cores I'm using because it's the number of threads that I'm running. So CPython, of course, is running multiple threads, but it's only ever using one core at a time. I really should label that threads, not cores. And then the y-axis, of course, is the number of seconds that it took. So just to drive home how bad this is, on 7 cores, CPython runs in 4.4 seconds, and the Gilectomy is running in 83.0 seconds. It is 18.9 times slower. As an aside, this is why, I got to say, I haven't been terribly gracious. Like, a lot of people like to talk to me and they say, well, have you heard about this super fast locking mechanism? That's not where the war is going to be won. The difference between 19 times slower is not, oh, you should use a slightly faster locking mechanism. There are major battles to be won here. Once I get it down to the point where it's kind of within shooting range of CPython, then I might be interested in more efficient locking mechanisms. Right now, there are more fundamental structural problems inside the Gilectomy, enormous nails that need to be hammered down, and that's where my head is at. So unless you're spending time doing analysis on the Gilectomy and saying, I found a super slow thing, did you know about this, Larry? Here's a way that you can make it faster. That would be super interesting. Oh, this is the way that Grand Central does logging. Not so interested. So let's start with where we were in last June. Like I mentioned, CPython uses Inker and Decker for reference counting, and I was using atomic Inker and Decker just to get the Gilectomy working. But this was 30% slower off the top, just using 2 threads, and it gets slower and slower. Each thread that you add is more overhead than the last. I think what's going on here, and I don't know for certain, but what I believe is going on here is that the cores need to talk to each other. There's an internal bus that they use to tell each other, hey, I'm doing an atomic increment on this thing, you need to not look at it right now. There's some internal bus that they're using to communicate with each other, and the more the more atomic Inker and Decker that I'm doing, the more traffic there is on that bus until we're starting to saturate the bus and people are having to wait. So getting that work not to be atomic would be a major win. It turns out, so first of all, I spent a lot of time thinking about this problem because I knew this was my hardest problem to solve. I actually came up with my own technique to solve it, and then I felt terrible because I was like, nobody invents anything new in computer science. Everything's been done. You don't want to invent something new. If you do that, you've probably done something wrong because all the good ideas have already been taken, particularly in multi-core, multi-threading. It's all the work was done a million years ago. So it turns out there's this book called the Garbage Collection Handbook, the second edition, just updated in the last couple of years. And it's mostly about garbage collection, what technically is called tracing garbage collection. But reference counting also counts as garbage collection. So they have a chapter in the beginning about reference counting, and then, turns out, they have a chapter at the end about reference counting in multi-threaded programs. And there are two things in this rather slim chapter. One of them was exactly the thing that I had invented on my own. The other one is something that's very complicated that I don't think we can use, called the recycler. To be honest, I don't understand how the recycler works internally. I got to sit down and just read this book, but I don't think we can use it. I think it requires like compile time support. But let's talk about this concept. What the technique is called buffered reference counting. So let's examine our problem. We have this object O at the top. We have 3 threads that want to talk to object O, and every time they want to talk to it, they want to increment the reference count, and when they're done talking to it, they want to decrement the reference count. So they're all trying to talk to the same area of memory, and that's why I have to use atomic anchor and decker. We'd like to make it cheaper. The way you make it cheaper is, let's have only one person talking to the reference count at a time ever in a guaranteed way, and then he doesn't have to use the atomic anchor or decker, right? How do you do that? Well, let's add a separate thread we're going to call the reference count committing thread. We're going to make a big log. We'll just wave our hands to say, this is memory, this is as big as we'll ever need it to be. It's a reference count log. It's like a transaction log for reference count changes. So now the 3 threads talk to that instead. Every time they want to increment the reference count on O, they write down O, add 1 to the reference count. Every time they want to decrement, they say O, minus 1 to the reference count. And then the separate thread sits there spinning, watching the log, and whenever there's work to do, it goes ahead and does it. Since the reference count committing thread is the only thread that ever touches reference counts, he doesn't have to use atomic anchor and decker. He can just modify the memory directly. As a matter of fact, it's a good idea if he's the only thread who ever looks at reference counts. Because one of the problems of this technique is going to be now reference counts don't happen in real time. Now reference counts, you don't know whether they're accurate or not. There could be reference count changes waiting in the log that haven't been committed yet. So this is going to cause some problems. I'll talk about it in a minute. But let's move on. This solves the problem of atomic anchor and decker, but all we've really done is change it so that now we have contention around this ref count log, where that has to be locked and unlocked per thread. But we can solve that. Let's have 1 ref count log per thread. So now each thread writes its reference count log changes to its own local log. Now there's no contention over the logs. They just need to lock a little bit between the commit log, the committing thread, and the individual threads, but you just take the buffer and pass it off. That's no big deal. This solves all the contention problems, but now we have an ordering problem. So let's walk through that. Let's say that we have 3 threads. We really only need 2 threads for this example. And let's say, for the sake of argument, we have a list, and that's capital L, and it has an object inside of it. I'm going to call it O. It's unnamed in this example. And list L has the only reference to object O. That's the only reference that exists. So O's reference count is 1. And all of those changes happened a million years ago. The dust is all settled, so it's nice and stable right now. So currently, O has a reference count of 1, and that reference is being held by L. Thread 1 comes along and says for X and L, print X. That does an increment and a decrement on object O. And then later, thread 0 comes along and says L.clear, blows away everything inside of L. That says O minus 1. That drops the reference to object O. So that's going to kind of look like this. In the reference count log for thread 1, we're going to have an O plus 1, O minus 1. And then later, in reference count log for thread 0, we're going to have an O minus 1. The problem is, what if we commit the reference count log for 0 before we commit the reference count log for 1? We're going to drop the last reference to object O. The object will be destroyed. And then we're going to later commit the reference count changes in thread 1, and we're going to say, oh, O plus 1, and now your program is no longer correct because you're touching an object that has been destroyed. Now you might say, well, just do those in the opposite order. The first thing I would say to that is, how do you know you were supposed to do them in the opposite order? And the second thing I would say is, what if I do this to you? Now we have 2 lists L and L2. We have 2 objects, O and O2. We iterate over the lists in 1 thread each, and then we clear the other list. There is no order that you can process these logs in where your program will be correct. Now your program is inevitably incorrect. So how do we solve that problem? One way might be to write down a timestamp every time we write down a reference count change in the log. That's expensive, and it may not even be correct. There's been bugs in the past with I would use the RDTSC instruction on an Intel x86, where that gives you a timestamp counter that's internal to the CPU that's very high precision, which is what I would need for this. But if you have actually two physical CPUs in your computer, like I have, sometimes they can drift, so the timestamp counters will be different. And that would be problematic. That would mean we would commit these things out of order. So it would be expensive and unsafe. We can solve this problem, but it takes stepping back and re-examining the problem itself. Because it turns out we don't actually need super strong ordering of reference count changes. We can do something much weaker that is much cheaper, and we can achieve that very easily. So let's start with this observation. Let's talk about two objects. Excuse me, let me get this right. Let's talk about two reference count change events. These are two events that we're going to write to the log. I'm going to talk about reference count change 1 and 2. And 1 might be an inker or a decker, and 2 might be an inker or a decker. And the question is, can I swap them in time? Is that harmless? And it turns out, 3 times out of 4, the answer is yes. If you have an inker followed by an inker, you can swap those, that's harmless. If you have a decker followed by a decker, you can swap those, that's harmless. If you have a decker followed by an inker, you can swap that, that's harmless, because they can't be talking about the same object, or if they are, the object is obviously still alive, because we did a decker, we assume the program is safe. If we did a decker and then we did an inker on the same object, I assume that that was safe because the object is still alive. The only one that you have to make sure that you keep in the same order is if you have an inker followed by a decker. If those are talking about the same object and there was only one reference to the object and you did that inker, that keeps it alive when you do a decker immediately afterwards. You cannot swap those. But all this is telling us is we need to make sure that any decker that happens after an inker in time has to happen afterwards when we commit it. And that's a lot cheaper to achieve. So here's what we do. We have 2 separate logs per thread. One for inkers, one for deckers. And all we need to do is queue them in such a way that anytime we process a decker log, we ensure that all of the inkers that could have possibly happened before it in time are committed first. I got this working, and then I iterated on the algorithm, and now I have a very safe queuing algorithm that is in constant time for everything. So this is working really well. As an aside, right here, this was an indispensable tool in working on the Gilectomy. This is called UndoDB. That's undo debugger. It is a reversible debugger where you can, it behaves exactly like GDB. And what you do is you set a breakpoint and you examine data and you're like, how the hell did we get in this state? And so you set a memory watch point and then you run your program backwards and you see when that triggers. It's like, oh, that memory changed in this way. Well, how did that get there? And then you set another breakpoint or a memory watch point or something, you run the program backwards some more. Indispensable for solving these problems because you can get in these situations where it's like, I have no idea how the program got in this state. Now you can run it backwards and find out. So I used UndoDB a lot in the development of the reference count manager. But let's talk about what has happened as a result. So this is the old macro in C for performing an incref. This is what adds 1 to the reference count. It's very simple and straightforward. We take the object, we find the reference count inside, and we add 1. It's more complicated now. So the first thing we do, you look at the bottom, I say PyIncref is incref1. Incref1, what it does is it goes to thread local storage and pulls out this reflog object, which is where we're storing our reference counts per thread. And it does an incref2 on the object now. So incref2 is implemented like this, where we say, is there space in the reflog right now for me to write another pointer? Oh, there is. Then I'm going to go ahead and write one. Oh, there isn't? Then I need to rotate the logs out, get fresh inker and decker buffers, and now I write the log. And then I have 3, which is unsafe, which just writes the thing directly. And the reason that I have 3 of these is because you can use, they get progressively faster. This is the really slow version. But I knew that it was going to be slow, and so I have this macro. It says pyrefcache. You put that at the top of a function, and now it's cached. I've cached the reflog that's for your thread as a stack variable, and now you can just refer to that all the time. So now you can change all your pyincref and pydecrefs into pyincref2 and pydecref2, and they're just faster for free. If you want to work a little harder, then you can sort of pre-ensure that there's room in the reflog for all of the thing you're about to do. If you're about to do 5 decrefs in a row, then you don't have to check each time, is there space? You can say, is there space for 5 decrefs? And if there is, then we just go, and if there isn't, then we do a rotate right then. That's a little troublesome just because it has to be right there. You can't recurse into the Python interpreter because that's going to do its own increfs and decrefs. So you need to make sure that this is very tightly coupled, but you can occasionally use this PyIncref and PyDecref3 by pre-establishing that you're going to have room in the logs. This isn't actually, it looks like a lot of code. It's actually pretty fast. It's really not a big deal. Like these temporary rows go away. All that PyRefPad is really doing is doing dereferencing a pointer, storing to it, and incrementing. So the other thing that this resulted in, the other problem that this caused, apart from making incref and decref a lot more complicated, is that there are a couple of places. There's one place I know of for certain where you really need real-time reference counts on an object, and that is weak refs. The way that a weak ref is implemented, I'll remind you that you can have an object, let's say object A, and then you have a weak ref object that's a separate object called, we're going to call that B, and B is a weak reference to A. You can say, hey, B, give me a strong reference to A. It's like get weak ref or something, or get ref. And it goes and gives you one. And the way that's implemented inside of CPython is A knows that there are weak refs pointing to it, and when A is destroyed, it calls all of its weak refs and tells it, hey, A is being destroyed, you're not legal anymore. And they say, oh, okay, sorry. But from a technical point of view, B has a pointer to A, but it does not have a reference to A. It does not actually know at any particular time whether or not A is alive. It's relying on the fact that we're running in the GIL, and A is going to tell it, oh, I'm dead now, to be safe. But under the Gilectomy, of course, we don't have the GIL. We don't have that safety. And so I had no way, because of these buffered reference counts, I didn't know in real time whether or not an object was alive or not. What I wound up solving this problem with was a secondary reference count that is only used for weak refs in a couple of these other special examples, which is atomically modified. It's actually not incred and decred. The way that it works is you read the value. If it's -1, the object's being destroyed and you're done. If it's not -1, add 1 to the value you got and do an atomic test, compare and swap. If that succeeds, then you've kept the object alive and you have a reference and you're good. If you get back a -1, then you know that the object's being destroyed and you can't modify it anymore. So that solved the problem for weak refs. I'm actually also using it for something called intermodal strings. People have said, Larry, you're using too big a hammer here. You can solve that another way. I'm using it right now, and I haven't worried about it because it's kind of a minor implementation detail. It's not a performance hit thing. But I got intermodal strings using the same technology. I don't think I need to. Finally, someone pointed out, again, I think the same guy, actually, Mark Shannon, pointed out, I have a problem with resurrecting objects. If you have a dunder-del method that takes self and writes it to an external variable that's doing an incref on the object, and that's going to keep the object alive, well, guess what? I don't know that the object's being kept alive. I don't have a real-time reference count, and I go ahead and delete it, and now there's a reference to this deleted object. I have no idea how I'm going to solve that. He says he has an idea. I don't believe him. So anyway, my advice is don't resurrect objects inside of dunder-del. That's never been a good idea in Python, and now it's an even worser idea. Actually, Jython and IronPython had to solve a lot of these problems themselves, so I can always talk to the IronPython and Jython guys and ask them. They said they have a solution that is terrible, but it works. So let's look at the graph. This is what happened as a result of making the reference count manager. So again, we have the same two lines. Red is always going to be stock CPython. Blue is always going to be the atomic version as of June. And this new green line, that's what it was like as of October. So it's getting faster. So then the next thing that seemed to be slow was the small block allocator, what I'm going to call obmalloc. And what I originally did was I had one big lock for just all of obmalloc. Because like you grab that and you can allocate memory and you drop it. And that was super hot right away. So internally, obmalloc thinks of, it calls these memory classes. So like, it's a range of bytes that you want to allocate. If you want to allocate 0 bytes, that's just illegal. I think it just always gives you a pointer back that's valid. 1 to 8 bytes is a class, and then 9 to 16 bytes is a class, and 17 to 24 bytes is a class. So it thinks of those internally as being separate. So what I did is I added per class locking, and that made it faster, but it still wasn't fast enough. So I added 2-stage per class locking. There was the fast lock, which is for the super fast case of, we have memory, we just need to slice it off and hand it back. And that's got its own super fast lock. It's actually spin lock. And then there's a slower, heavier lock for, oh, I need to go and talk to an arena, or I need to actually go allocate memory or whatever. Anything that isn't the super fastest thing allocates a second, heavier lock, which doesn't prevent other threads from doing the faster thing if that actually happens to work for them at the time. That sped things up. I also added a per thread free list for generic allocated memory that's stored in thread local storage, and that sped things up again. And finally, around this time, I also went through, I gather a bunch of statistics when I'm doing debugging of the Gilectomy, and I turn that on, and that slows things down immensely. And I did a conscientious job of making sure that there was absolutely no overhead from statistics when statistics were turned off, because I was pretty sloppy about it before. So as a result, it definitely got faster. The problem is it doesn't show up in the graph. I don't know what happened here. When I ran these benchmarks, you can tell this is janky. You can also tell it's above the green line. It really should be below. I guarantee you, I swear, it was faster when I was done, but I don't have the data to show for it. I'm sorry. I don't know what I did. But get used to it. You're going to be staring at that yellow line. So that's as of February, I think? Yeah, no, that's as of April of this year. That's as far as I took it. I took a break for a couple of months. I was just tired of working on it. But I came back to it. And the next thing that seemed to be slow was the physical act of pulling things out of thread local storage. So I'm going to show you a little bit of CPython internals here. The function that actually runs bytecode is this one gigantic function called pyeval_evalFrameEx. That's the guy who literally runs bytecode. So I needed to pull out my thread local storage variable in order to look at stuff inside of that. So at the top of the function, I say pythread_state equals tstate equals pythread_state_get. That goes to thread local storage, pulls it out, sticks it in a stack variable. Then, whenever you make a recursive function call, it calls a function called callFunction. CallFunction needed that tstate, so it pulled it out. And then that recursively calls another function called fastFunction. FastFunction needed that thread state thing, and then it calls pyeval_frameEx. These three functions get called every time you make a function call in CPython. And the Fibonacci benchmark is nothing but recursive. So I'm making millions of recursive function calls all over the place. And every time I do it, I'm looking in thread local storage 3 times. So I was making 370 million calls to pthread get specific, which seemed to be at the top. It wasn't dominating runtime, but it was an enormous piece of runtime. And I wanted to get rid of that. That's pretty straightforward, actually. All I did is I sort of added an external membrane. I took all the existing functions and I added a 2 to the end. Again, the Gilectomy, we're not going to merge this. We're going to do a proper job if it makes it into CPython. But just to get it going, I added a 2 to the end of all these internal functions, these 3 function calls. And then I made the externally visible one, evalFrameEx, I made that so that it looks up the thread local storage thing and passes it in as a parameter. And now pyevalFrameEx2 takes it as a parameter. CallFunction2 takes it as a parameter. FastFunction2 takes it as a parameter. Now we only look it up once, and we can do 8 million recursive function calls. So we're fine. That sped things up again. So this is where we are today. This black line, that's what I'm calling the no TLS line. You'll notice that it is faster still than any of the previous lines. It is getting faster and faster. Now I want to draw your attention to the fact this is the CPU time graph. So this is the collective amount of CPU time I've spent across all 7 cores at the right side of the graph, as opposed to CPython, which is only using 1 core. But what I said at the beginning was, I'm actually interested in wall time. I'm defining success or failure on this in terms of wall time. So here's the wall time graph. Guess what? The black line looks a lot better now, doesn't it? I'm pretty close. Again, the benchmarking is so terrible. And the CPU cores are changing frequency. The ground is shifting out beneath my feet. I don't know. It could be that I'm actually faster. Probably not. It could be that I'm slower than that. That's more likely. But I'm within striking distance. And I feel like if I find another big thing that's a problem, I may actually start to dip below it now and then, at which point I'll say, the Gilectomy is a success, everybody. So the next thing that I'm working on obmalloc again, because I think it's still dominating runtime. At one point, I switched obmalloc to using spin locks instead of my futex-based locks. And the futex locks, I ran under the profiler. And allocate memory was 20% of runtime, and free memory was 20% of runtime. That doesn't show up when I use the futex-based locks for some reason. I don't know. Maybe cache grind doesn't like me. But I'm like, if I change that lockout, the runtime doesn't change significantly, but the graph changes. I suspect that maybe it's like, I think it's still using the time. It's just not showing up in the profiler. So I want to rewrite obmalloc so that there's a central first data structure that's called used pools, and that's global for the entire process. I want to make that per thread. And actually, technically, I did make it per thread, and now it's not working properly, and so I run my benchmark, and instead of using 200 megabytes, it uses 10 gig before it's done. And the physical act of allocating and freeing 10 gig worth of objects, or whatever it is doing underneath, itself is slow, and so the whole program got a lot slower. Once I figure out what that memory allocation problem is, I can make that go away. But I still have another experiment or two to try. I have an idea I call private locking. You start with the observation that all objects, most objects, when you never leave the thread they were created in. And so, if we create a dict and it only lives in a single thread and then it's destroyed and never escapes that thread, then why do we have to lock and release every time we talk to that dict? It'd be cheaper to do something else where we knew that it was a per thread object and we didn't have to do all that locking. So I have an idea that essentially dicts and lists and other objects like that are created in this sort of pre-locked model where if another thread wants to talk to it, it has to say, hey, I actually want to talk to this. You need to turn it into a regular lockable object. And before that, locking and unlocking would be a simple local non-atomic increment and decrement. I tried it once, it made it slower. But, like I said, I may turn the corner and I may figure something out, and maybe I botched it the first time. If I try it again, maybe I'll get it to be faster. The other idea I have, this was implemented for me actually by Thomas Wooters at the sprints last year. He did something where he was at work where they store the reference count outside of the object. So right now, the reference count is stored right at the top of the object. And the reason that this might help the Gilectomy is because of cache lines. Every time that you change memory, that invalidates that cache line for all of the other cores. So if you have 8 cores in your CPU, all looking at the same cache line, you change that memory, suddenly it tells all the other cache lines, hey, you have to throw away your memory and get a fresh copy because it's changed. And since we're storing the reference count in the object, that means that we're changing the memory on every object in Python anytime we examine it, including objects that are otherwise immutable, like, say, an integer or a string. So again, the Gilectomy is doing nothing but integers, and every time it examines the number 0 or 1 or 2, it's invalidating the cache lines for all the other cores. If we could get it so that these objects were genuinely immutable, then they wouldn't blow away those cache lines. That would get rid of contention on this internal bus where the cores are talking to each other. It seems like it actually would be better for copy on write semantics for when you were doing multiprocess, although again, the goal of the Gilectomy is to make it so you don't have to go multiprocess. But storing the reference count outside of the object itself is overhead, and it made it slower. But maybe in the future, maybe we'll figure out a better way, or maybe I just botched it, and maybe it'll be faster in the future. It certainly might help with copy on write semantics. We'll see. If all else fails, I have one more huge thing that I can do. This was suggested to me by multiple. This wasn't my idea. This was Mark Shan and Wukash both suggested it independently. The idea is everybody knows that tracing garbage collection is faster than reference counting if you want to do multi-threaded, and that's what everybody does these days. Like Java is tracing garbage collection, Rust, Go, everybody these days. All the new languages are all tracing garbage collection. So we switched CPython internal to use tracing garbage collection. This is a more difficult API to get right. It's going to break the entire C API, but there's a technology inside of PyPy called CPyExt. PyPy, of course, you know, is the Python that's implemented in Python, and it uses JIT, and it uses real tracing garbage collection. It doesn't use reference counts. So their object model is very different from CPython, but a classic problem for PyPy is that it doesn't run C extensions. They had an idea where they could run C extensions unmodified, like you literally could use a compiled shared library and just plug it into CPython to PyPy. But what they would do is simulate the C API, and that involves simulating CPython's object model, which involves simulating reference counts in a tracing garbage collection environment. We don't have their problem of their internal representation of an object is very different. So what they had to do eventually was they had 2 different objects. There was the actual internal PyPy object of whatever it was, and then there's the CPyExt representation, and they kind of had a problem keeping them in sync and stuff. We don't have that problem. We can just use the internal CPython object without the GIL, and CPy extensions can talk to that, and we would just simulate reference counts on top of it. That'd be pretty harmless. And so it would be a lot simpler for us. And all we need to do is simulate reference counts, and we could probably get that working. That'd probably be pretty close. Again, we can't guarantee no breakage on the C API, but we could actually do some things to mitigate the multi-threadedness of the Gilectomy, and we simulate reference counts, and we could get away, perhaps, with running CPython extensions in this Gilectomy version with tracing garbage collection. That'd be a lot of work, and I really don't want to do it. So I'm going to try and push this existing approach as far as I can, but if I really have to give up, maybe I can start over and do this. So the final thing I want to talk about is just, this is what we want to see. This is the graph we actually want to see, right? I just drew this purple line here. The idea is you add threads to your program, and it just uses multiple cores and doesn't care. The program doesn't get any slower. This is what we wish we had, right? Actually, we have that because that's Python. And what I say is that Python and IronPython are actually existence proofs that the Gilectomy will work, because, consider, let's just say that we have a whole pile of C code, and it just happens that like one of the piles is a Python, is a Java interpreter, and the other one's a CLR runtime. But it's a big pile of C code, essentially, and at the end of the day, they have a Python interpreter that's running multi-threaded without a GIL. This proves that you can write a multi-threaded Python interpreter in C without a GIL. The question is not, can we write one? Will it work? The question is, how much of the C API do I have to break before I can get the Python to work without a GIL? Thank you.
Larry Hastings, ladies and gentlemen. Now,
by the way, I have stickers.
Lunch is happening at the moment, so if you are wanting to leave for that, can you please do so quietly? If you have questions for Larry, there are 2 microphones here in the aisles. Please line up, and please be quiet if you're walking out.
What I say is you can have one of each design of the sticker.
Okay,
Please
we have
don't
a
take more than
question
one if you
here
want one.
on my right.
Hi.
Yeah, Larry can hear you.
I can hear you. Go ahead.
So some of this sounded very Intel and architecture specific. Is there, when you think about ARM CPUs or running Python in other environments, do you expect that this approach will be feasible in those places as well?
People in the audience, can you please be quiet? There are questions and answers happening and people are still trying to listen.
Okay. I heard everything you said. Is that your whole question?
The question is your approach to this going to be usable in other architectures like ARM? You talked about Intel-specific CPU instructions.
Right. So the answer is it should be. Right now it's not. Literally, so like I said, I discovered about, a friend of mine told me about a week ago, oh, did you realize that your cores are changing speed on you? I said, oh my God, no. So I wanted to test on something that I had handy that I knew was multi-core and I guessed was not going to be sophisticated enough to change the speed on me like that. So I tried compiling the Gilectomy on a Raspberry Pi 3. Which is 4-core and ARM. And it didn't work because it's, first of all, I had one problem, then I fixed it, and I had another problem. And then I said, oh yeah, I can include this x86 internals header file. That was something that GCC had given me. And so I was like, okay, I can't solve that. But all of the atomic instructions that I'm using, I talk about Intel-specific things. RDTSC, of course, is Intel-specific. I'm really only using that for statistics gathering. I'm not using that as an implementation base of the Gilectomy. Every modern architecture does have atomic increment and decrement. Every modern architecture has atomic test and set or compare and swap instructions. So all of those things should be portable. There will be more platform reliance in the Gilectomy because we have to use those things, and that's not part of the standard C API, but they're all available. And so all we need to do is a little bit more platform hacking in order to get those to work.
Next question.
Okay, so basically you said that benchmarking is really bad. Everyone knows this. So how worried are you like that the fib function isn't good enough? I mean, if you tried any different function or anything else, that the results would be completely different. Like how worried are you about that? Have you tried?
I don't think it'd be a world of difference. Again, so this is specifically exercising. I had a list of all the things it's exercising. So for example, someone suggested an optimization to me. They said, the Fibonacci function itself, looking up the Fibonacci function takes a lot of time because we have to do a dict lookup and actually has to look in the module, so it's not cached locally. So it needs to lock and unlock a dict, and that module dict itself was hot. And so if we did multiple reader, single writer lock on the dict, that would speed it up. And I said, well, on the one hand, I think that's optimizing for my particular benchmark. Let's not do that. But on the other hand, that's a generally that's a helpful optimization for a lot of people. And it really isn't all that's tailored to my code. And it would work on all dicts. And it'd be fine. So I think ultimately we're going to merge that and make that benchmark faster. Of course, we wouldn't see that if we went to a different benchmark, like the one that David Beasley uses when he's timing things and playing with the GIL. He uses countdown, which is just a for loop over 10 million times or something like that. So At the end of the day, I'm not all that worried because fundamentally I'm exercising bytecode, I'm exercising function calls, I'm exercising dict and list lookups internally. I'm exercising a little bit of Boolean logic, I'm exercising integers, not strings. But all the things that are implemented in C, I'm not that worried about. I'm worried about the internal core bytecode engine, really, of CPython is what I'm worried about. And one function is as good as another at that point. So once I'm more confident about the Gilectomy and the approach, then I'd be more interested in running more code through it anyway. But right now, I just have my head down. It's like, if I could make Fibonacci run faster than stock CPython, then it becomes much easier to make other things run faster than CPython. So yes, eventually I'll run other benchmarks, but not now.
Another question?
So if I understand your ref count log implementation correctly, it would actually truly make like del invocations like actually non-deterministic. I've unfortunately seen a lot of Python code that kind of relies on reference counting, even though that was never really guaranteed by the actual implementation per se. But if you did go forward with this plan, I could see code breaking because they relied on that reference counting implementation. And I guess what is your like...
Okay, so you're talking about...
how do you go forward with that?
You're talking about the fact that people rely on, you're not talking about reference counting per se, you're talking about the people that rely on the fact that once the last reference to an object is dropped, that the object is freed immediately.
Correct.
Right. The Python language spec specifically says you're not allowed to rely on that, and none of the other implementations make it happen, and that's just a fact of life. That is a Python visible side effect of the implementation of the GIL, and if we ever merged it and became official Python, then yes, it would go away, and I'm sorry. So that's why we have things like context managers. The context manager is explicitly there for this sort of object lifetime management.
Oh, exactly.
Yeah, can't do anything about it. Sorry, I can't help you.
All right.
Another question?
I thought you were going to bring up another topic, which I didn't touch on really quickly. One side effect, the original implementation of the reference count manager, of course, it was doing the incers and deckers on this other thread, right? Which meant that the last decker happened on that other thread, which meant that dealloc happened on that other thread. And so now that's two effects. One, deallocs happen on a different thread from where the object was originally, like where it would have naturally happened. And two, that meant that the dealloc thread, the commit thread, had to work like a pit pony. It turned out that that just swamped it. It was spending all of its time doing deallocs, and it fell behind immediately and never caught up. So what I wound up doing internally is when the object reaches a reference count of 0, I put it on another list, and I pass it back to the last thread that did the last dec ref, and then he notices that later, and he commits it. So there is another delay built in before the object is destroyed. So it's even worse than you probably thought.
Next question, please.
Just another quick question about benchmarking.
I don't have, quick question, it'll probably be a long answer. I'm sorry.
I think this, assuming that speed step is just for reducing power consumption, is there not a BIOS setting to turn it off?
Yeah, so I went through my BIOS and tried to turn off everything, and I guess maybe I had a lame BIOS or I was looking in the wrong spot, but there was literally no big flashing, set your CPU frequency here thing. So I turned off AI turbo boost or something like that. There were about 3 things that I turned off, and it seemed to be a little bit more stable then, and so these benchmarks actually run with those settings turned on. But apparently, Victor said there's literally a Linux kernel setting where you can specify the max frequency. And so if I said, oh yeah, your max frequency is a gigahertz, then guess what? Everybody's going to run it at a gigahertz, because that's like slower than it ever wants to be. So I'm going to do that once I figure out what that setting is, and once I get home and I'm sitting in front of the computer again. But like I said, I'm only in so much of a hurry about it because I'm in the neighborhood.
Okay. Last question.
Do you have an idea how much you can minimize the C API changes from this by the time you're all
How
done?
much I've what since the API change?
How much the C API changes will be to write or to
Okay,
use
so
this?
I kind of answered that question in my talk from last year. The answer is that so far I have essentially preserved the existing source code level C API. So a recompile would get you using all of the new technologies underneath, and you didn't have to touch the line of source code. The problem is that there are semantic changes involved. So there are guarantees that the GIL gives you that I don't give you. And there are other things happening, like what he alluded to, which is the instantaneous objects going away, being able to rely on that, which you don't have anymore because of buffer reference counting. So another example of this, which there's literally an example of this as a good approach to how to do things in the CPython extension documentation. They say, here's example code. They say, let's say you have an object and you want to lazily instantiate it because it's expensive. You only want to do it when it's needed. So you say static PyObject star foo equals null. And then you say, inside of the middle of your function, you say, if foo is null, create foo. And now we can use foo, and everybody's happy. The problem is, if you called that 3 times, now you've got 3 races. And probably you're going to allocate memory uselessly, and you're going to stomp on that value. And that used to be safe because it was protected by the GIL. Literally nobody could interrupt you and call into that again. But without the GIL, that's no longer safe. And so I would say, don't do that. But there's lots of code that does that, and it's a guarantee that the GIL gave you that I've taken away. So that's a semantic change to the API that isn't encoded in the actual, like, literal Py, incref, PyDecref. Those things haven't changed, but the semantics around them, of stuff that you've been doing for years, have changed. And so that's why I say I know I'm going to break C extensions, because these semantics have changed, and I can't do anything about them. The whole point was to break those sorts of things, and I can't fix that. In terms of source code compatibility, literally my goal is that you can recompile and you will produce, like, you won't get any errors, and there are no new APIs that you were supposed to call that you didn't. Your code will continue to work. And there are additional APIs that will make things go faster, but unchanged, C APIs should physically compile.
Larry Hastings, everyone.
Reference counting for tracking the lifetimes of objects, and I switched that to atomic increment and decker. That's something that your Intel CPU does for you, where it will increment or decrement a number stored in memory in an atomic way, such that there are no race conditions. You're guaranteed that after you're done, the number has been incremented by 1, and it was done in a safe manner. I used I added locks to all the internal data structures inside of Python objects that are mutable, like dicts and lists. So that those operations are safe. If you append to a list or you add set an item on a dict, that has to be an atomic operation. It has to be safe. And so those objects lock themselves internally. I also added a bunch of locks around a bunch of internal C data structures that are used inside of CPython, like free state. But there's 2 in particular I want to call out. Obmalloc, which is what we call the small block allocator. This is used for memory allocation for small objects, which is like under 256 bytes or something. I don't remember what the cutoff point is. But this is used for most of the objects that are allocated inside of CPython. And this is very finely tuned, and it's super fast. And CPython relies on it being fast. And adding locking to that in order to make it safe has slowed it down a great deal. Also, there are a bunch of free lists inside of CPython. It's very handy if you're using a bunch of, say, integers or
past. So it's time for our last talk before lunch, everyone. So we really should make a start now. Our next speaker is here to talk about the Gilectomy and how it's going. Please make welcome Larry Hastings.
Thank you. My name is Larry Hastings. Ladies and gentlemen, boys and girls, children of all ages, this is the Gilectomy. How's it going? PyCon 2017 edition. I call the talk that because when I go to conferences now, people walk up to me and say, oh, Larry, oh, you're the guy working on the Gilectomy. How's it going? And I'm like, I'm about to speak for 40 minutes about how the Gilectomy is going, and I don't want to answer for 40 minutes every person who walks up to me at a conference. So I'm going to do it for everybody all at once, and now you don't have to ask that question. You can ask a more specific question. So about this talk, I want to warn you, just like last year, I gave a talk about the Gilectomy last year, an introductory talk. This is kind of the same preface slide. This talk will be exceedingly technical, and it's going to assume that everybody in here is comfortable about me talking about multi-threading issues and about CPython internals. This year, it's a recursive Fibonacci. So this is exercising an if statement. It's exercising some math. It's exercising recursive function calls and, of course, bytecode and a bunch of internal stuff inside of the Python engine. But this is all I ever run. So I'm running on this on multiple cores simultaneously inside of CPython. So an overview of what's happened since last year when I gave the Gilectomy talk. We start with what I'm going to call last June's version of the Gilectomy, the atomic version for using atomic increment decker. I switched to something called buffered reference counts, which was done by about October. And then I did a bunch of work on obmalloc, and that was done in about April. And then just this month, I did some work that I'm calling no TLS. TLS, when I say TLS, what I mean is thread local storage. This is data that you can store per thread so that each thread has its own version of something. You need that in order to, you can store something there and no other thread is going to examine it, and so you don't have to lock it in order to talk to it. So I'm going to go through each of these items and basically what it is, and I'll show you how much it got faster. But I want to talk for just a moment about how benchmarking is impossible on modern computers. As Victor talked about in his talk this morning, modern CPUs, like an Intel CPU, a frame object, if you allocate a fresh one every time, that's a little slower than just say, oh, the last one that I use, I'm going to put it on the list and then reuse it next time I need a frame object or an integer or something. So there are a bunch of free lists internally of Python objects that get reused constantly. And I, of course, had to put locks around those data structures or make them per thread. I also disabled the garbage collector entirely. I'm just not ready to deal with the garbage collection under the Gilectomy. There's a lot of research. There are absolutely thread-safe, multi-threaded friendly garbage collection algorithms. That's going to be a lot of work, and that's not the thing that interests me. What interests me is getting Python to be fast enough that this is useful for somebody ever. So my general approach is I got it working, and now I figure out what the slowest thing is, and I run it under a profiler, or I come up with thought experiments, and I experiment, and I try something, and I see if I can make it go faster. If I make it go faster, then I keep it. If then it doesn't go faster, then I don't throw it away. I may like put it on the back burner and try it again later, because sometimes you turn a corner, and now this technology is going to work again. Just to give you an idea of how crappy this project is, my official benchmark that this is literally all the code I ever run under the Gilectomy is a really bad Fibonacci number generator. I'm kind of assuming that you're mildly familiar with like maybe my talk from last year. So there's a lot of stuff that I'm not going to explain. I'm just going to dive right into some of these concepts. If you want to know more, you can watch my talk from 2 years ago, Python's infamous GIL, where I explained the GIL itself. And then last year's talk, where I kind of got started, the Gilectomy removing Python's GIL. So the GIL, the goal of the Gilectomy, or the GIL of the Gilectomy, I want to run existing multi-threaded Python programs. So a Python program you could write today using the threading module. I want to run it on multiple cores simultaneously. I want to run it with as little I want to implement this with as little C API breakage as possible. It's impossible to not break the C API. There are some guarantees the GIL gives you that I cannot guarantee anymore. But with as little breakage as possible. And I want to run it faster than CPython does with a GIL by wall time. So this is if you had a stopwatch and you started your program running, when it finishes and you hit it again. If the program ran faster, then I will declare the Gilectomy a success, which it has never done. The approach that I'm taking, and again, this was most of the talk last year, Python uses